Section 7.3, Elimination using addition and subtraction. So in this lesson we're going to look at another algebraic method for solving a system of equations. Remember, we've already looked at graphing a system to find a solution. We've looked at substitution, and this is our third method, elimination. Sometimes adding two equations together will eliminate one variable. This allows you to find the value of one of the variables and then use substitution to find the value of the second variable. So elimination. My key word for that is to line up like terms. Remember, in substitution I said you should set them side by side. So substitution, side by side. Elimination, line up like terms. So write down the 4 steps and then we'll do them together. So the first step, set the equations on top of each other so that the like terms are in the same position. I'll show you what I mean by that in just a second. Second, add or subtract the equations so that one of the variables is eliminated. Third, solve for the remaining variable. And last, we're going to use substitution. Once we have one variable's value, we can certainly find the other. So let's look at this. So here are my two equations. So instead of leaving them side by side like I did for substitution when I worked back and forth from one equation to the other, I'm going to line them up, and when I do, I'm going to make sure that the variable terms are on top of each other. So the x's are in line with the x's, the y's in line with the y's, and the constants are lined up as well. And we were fortunate that these two equations were already set up in the same order, standard form, so that it wasn't too tough to do. So now what I'm going to do is I'm going to add these equations together. 3x plus 2x is 5x. Negative 5y and positive 5y become 0. And negative 16 plus 31 is 15. Now I have a fairly simple one variable equation. Divide both sides by 5 and I get x equals 3. So then the third step said, the fourth step says now take the value of this and substitute it into one of the equations. It doesn't matter which one we pick. I'm going to go ahead and just pick the first one. 3x minus 5y equals negative 16. In place of x, I'm going to put in my 3 because I know one variable, and now I can find my second variable if I keep working. Oops, 25, and divide by negative 5 and I get positive 5. So my solution is x is 3 and y is 5, or the ordered pair 3, 5. So if I had graphed these two equations on the graph paper, they would have intersected at the ordered pair 3, 5. It's always a good idea to check your solution. So if I check this back into both equations, 3x minus 5 equals negative 16, putting in 3 for x and 5 for y, I will get 9 minus 25 equals negative 16, so that one works. Checking the other equation, and again putting in 3 for x using these two ordered pairs and 5 for y, I get 6 plus 25 equals 31, and that's true as well. Okay, let's try another one. I want you to try this one on your own and then you can come back to the video. Okay, so you should have done this. Let's give it a try. I'm going to start by lining up the like variables. Let me make sure I'm good here. So, oops, sorry. Okay, 3m minus 2n equals 13 lined up with my other equation. Add my equations. 4m equals 10. Whoops, I'm sorry, that was 13. That looks better. 20. So n equals 5. goodness, m equals 5. Then I'm going to substitute that back into one of the other equations. I'm going to use the bottom one this time. It's a little simpler equation. So plugging in 5 for m, I get 2n equals 2 and n equals 1. So mn xy, the ordered pair would be 5, 1. And again, you can check it in both equations. Now I want to just take a minute and show the substitution method, okay, because that's what we did before. And again, it doesn't really matter what method we use. And again, if we had graphed this on an xy, 5, 1 would be the place where the graphs would meet. All right, so substitution. I'm going to solve this equation for m. I'm going to substitute this back into this side. 3 times 7 minus 2n equals 13. So that's 21 minus 6n minus 2n equals 13. Negative 8n, if I subtract 21 from this side, I would get negative 8, and n equals 1. Substituting that back into the original, m plus 2 times 1 equals 7, m equals 5. So I hope you can see that it doesn't matter what method I use. If you had wanted to take the time to graph these, as I said, again, they would graph at the point 5, 1. And I want you to see also how lining up the like terms works great for elimination, setting the equations side by side for substitution so that I can work back and forth from one equation to the other. Okay, this is an example of the type of word problem you're going to see. Twice one number added to another number is 18. 4 times the first number minus the other number is 12. So I'm going to make my first number x, my second number y. So twice x added to y equals 18. 4 times x minus y equals 12. I'm going to use elimination, so I'm going to line up the like terms. I'm going to set these on top of each other. I'm going to get 6x equals 30. The y's have canceled. X equals 5. Plugging it back into either equation, I'll go ahead and use the top one. 2 times 5 plus y equals 18, and y equals 8. So my solution is x equals 5, y equals 8. So the first number is 5, the second number is 8. And we can go back and test that. Twice the first number, that would be 10, plus the second is 18, that works. 4 times the first, that would be 20, minus the other one would be 12. Sometimes elimination can be done with subtraction. 5s plus 2t equals 6. If I line these equations up, if I tried to add them together, I would not eliminate a variable. I would get 14s plus 4t equals 18. In order to eliminate a variable here, I have to subtract the bottom equation. So 5s minus 9s is negative 4s. 2t minus 2t is 0. 6 minus 12 is negative 6. So s equals negative 6 divided by negative 4, which is 3/2. Substituting that into one equation or the other. So 5 times 3 over 2 plus 2t equals 6. That's 15/2 plus 2t equals 6. I'm going to subtract 15/2 from both sides. 6 minus 15/2 is 12/2 minus 15/2, so that's going to be negative 3/2. And then if I multiply both sides by 1/2, I get t equals negative 3/4. So there's my solution, 3/2, comma, negative 3/4. Now, Sometimes we see that equations don't work out as nice and neat as we would like. And if we had graphed this, we certainly would not have found a good solution for this with a piece of graph paper. Okay? So here's another one. Try it on your own. And you might have to use subtraction here. Okay, x minus 3y equals 7. X plus 2y equals 2. I'm going to subtract x minus x. Negative 3y minus 2y is negative 5y. 7 minus 2 is 5. So y is negative 1. I'm going to put that back into my top equation. Again, it doesn't matter which one I pick. So x plus 3 equals 7 and x equals 4. So 4, negative 1 is my solution. Here's one more. This one's a little trickier because things are not set up exactly the way we like them to be. So the easiest way to do elimination is to have my equations in standard form. So the first thing I'm going to do is bring this 8 over. 8x plus y equals 1. I'm going to subtract the 3y on this side. So now I can line these up. I'll bring this one over here and subtract again because the 8's are both positive. So y minus a negative 3 is like y plus 3, and 1 minus 1 is 0. Oh, that should have been a 3, I'm sorry. That makes more sense. So that should be a negative 2. So y equals negative 1/2. Substituting that in, I'm going to substitute that into the top equation. 8x minus 1/2 equals 1. 8x equals 3/2. Multiply by 1/8, and x equals 3/16. Again, not a nice neat solution, but with elimination, instead of using graphing, we can get that solution. Substitution would have worked as well. Okay, we're going to look at another word problem now. This is the last thing on the video. In 1999, the U.S. produced about 2 million more vehicles, that's added to, than Japan. Together, the two countries produced 22 million. How many vehicles were produced in each country? So I need a variable for each country. The U.S. will be X, Japan will be Y. So the U.S., X, produced 2 million more vehicles than Japan. So they did the same as Japan plus 2. The two countries, X plus Y, produced 22 million. Now, if I want to use elimination, I need to bring this y to the other side. X minus y equals 2. I'm going to line it up with my other equation, and I can add because my y's are opposites. 2x equals 24, so x equals 12. Substituting that back in, I'm going to use this equation, and I see that y equals 10. So the U.S. produced 12 million vehicles, and Japan produced 10 million. Okay, so that's it. I did a bunch of examples for you because some of you asked for that, so we should be finished.